So now we're going to talk about the last bonding theory that we'll cover, molecular orbital theory. And so this is sometimes abbreviated MO, molecular orbital. As the name suggests, this calculates an orbital for the entire molecule instead of for individual atoms. Of course, it's impossible to solve the Schrödinger equation even for a very simple molecule like H2. But you can sort of do an iteration, trial and error process. You can use a trial function as an educated guess to see what the solution might be, and then you can adjust that and find the lowest energy. And so the computers are used to do that, and the math there is just way beyond what I know how to do. So we're not going to get into the quantitative aspects, but if you like hairy math problems and computational chemistry, that's something you could work on. So they optimize the trial function for the lowest energy, and that's what allows us to predict what the molecular orbitals are. Of course, we can never do better than nature. So these molecules form, and they form the lowest molecular orbitals, lowest energy molecular orbitals. And so what we're going to do here is we're just going to try to skim the surface and describe the basic ideas of this theory. So LCAO stands for linear combination of atomic orbitals. And this is a weighted linear sum of the valence atomic orbitals of the atoms in the molecule. And it is the simplest trial function for the Schrödinger equation that works fairly well. And it's the easiest to understand. Basically, it's combining orbitals, right? So we combine the valence atomic orbitals of all the atoms in the molecule. When we looked at valence bond theory, we were only looking at orbitals on a single atom, and we were hybridizing those orbitals, combining them. Here we're combining the orbitals from all of the atoms in the molecule. So these orbitals are delocalized over the entire molecule, whereas the hybrid orbitals remain localized on a single atom. So we'll see that molecular orbital theory can explain some things that even valence bond theory chokes on. Okay, so we're going to just look at some very, very simple molecules here. Let's start by looking at H2, 2 hydrogen atoms. So here's our first hydrogen atom. It has an electron in the 1s orbital, and our other one has an electron in the 1s orbital. And we're going to do a linear combination of these atomic orbitals. So here it would be an equally weighted sum of these orbitals. And so if we add these two together, we get a shape like this. This is called a sigma orbital based on its shape. And how do you see that? Well, imagine that you are a person standing down here, be an incredibly tiny person, right? And you're looking this way down that orbital. It's kind of like a sausage, right? It's round if you look at it from the end, just like the letter sigma is round, okay? So this is a sigma orbital, and it's called 1s because it's made from 2 1s orbitals, okay? This one is going to be a bonding orbital because the energy is lower when these two are combined than the individual orbitals were. So here we're representing the relative energy of these orbitals, and then when they combine, the energy goes down. Now, orbitals have phases, just like waves have phases, positive phase and negative phase. And so that previous one, we were adding 2 orbitals that were in phase. Here we're going to add orbitals that are out of phase. So we're going to add a negative. So this is like subtracting, it's adding a negative. So here we're taking these two orbitals. One has a positive phase and one has a negative phase, and so when we add them together, they have more of a destructive interference. And so they're going to form an orbital that's shaped like this. It's going to have a positive node and a negative node, a positive lobe and a negative lobe, and there's going to be a big node in the middle where there's zero possibility of finding the electron. This orbital is going to be higher in energy than the original orbitals, which does not promote bonding. In order for bonding to occur, the electrons in those orbitals need to have lower energy than they did as individual atoms. So we call this an anti-bonding orbital. It's still a sigma orbital because if we looked at it from the end, we're looking this way, it's still going to look round. But we can't see all the details. It's actually like two round things with a gap in the middle, but looking from the end, it just looks round. And so that's why it's a sigma orbital. So sigma 1s, because it's also composed of 1s orbitals, and then we put an asterisk here to indicate that it's an anti-bonding orbital. So sigma 1s is bonding, sigma star is anti-bonding. Any questions yet?
There's two types of bonding when it comes to linear combinations, positive, negative.
Yeah, when you put these two things together, you can get constructive interference or destructive interference. And so when they go together constructively, it lowers the energy, and destructively, it raises the energy.
So the first example is?
Constructive interference. Yeah. So adding. And this is like subtracting. It's adding the opposite phase. There's a star, yeah, an asterisk. It's maybe a little bit small. Yeah.
For these anti-bonding ones, this example chooses 1s minus 1s, so it would be, I guess, essentially 0. Would that happen for all of the anti-bonding ones, or would compare everything?
Well, it does seem reasonable that a 1s minus a 1s would be 0, right? And yet, it isn't really 0, right? We get this weird thing, which does not promote bonding at all because there's no place between, see these dots are the nuclei. There's not much between where the electrons could be, and there's a lot that's away from, and so it actually works against bonding. So I understand, we would think that we subtract them and they end up being 0, but they're not actually 0 because it's a little more complicated than that.
So if we subtract the orbitals, is it always going to be anti-bonding?
Yes. Yeah. So we're going to look at adding two orbitals in phase. That'll give us a bonding. And adding those two orbitals out of phase gives us an anti-bonding. Because again, if we start with two orbitals, when we combine them into molecular orbitals, we still have to have two orbitals. Because there has to be the same room for electrons that there was in the individual atoms. Same space, places. So here again is, this is an illustration of adding in phase. So we've got constructive interference here, and so we're going to get a bonding orbital. And here we see a lot of electron density, or the region of probability between the nuclei is large. And adding these out of phase, then we get destructive interference, and there's a node in the middle, and these are going to be anti-bonding. They're higher in energy, and that node is a region of 0 electron density between the nuclei, which works against bonding. So when we look at these linear combinations, we can look at something called the bond order, and we're just going to talk about diatomic molecules. The bond order is the number of electrons in bonding orbitals minus the number in anti-bonding orbitals, and then divided by 2. So for hydrogen, the bond order would be, there'd be 2 electrons in the bonding and 0 in the anti-bonding, and so then divided by 2, that equals a bond order of 1. Yeah, I skipped this slide. That didn't make sense. Okay, here's a molecular orbital diagram. So again, energy going up. Here is the orbital diagram for a hydrogen atom. It's got 1 electron in a 1s orbital. And here's the atomic orbital for the other hydrogen, 1 electron in a 1s orbital. And exactly how you draw the arrow here is not going to be important. Here they've drawn this one spin down because when it comes over here to pair up with this one will be up and one will be down. So instead of making it flip as it goes over there, they just drew it upside down. So the combination of these 2 orbitals gives us 2 new orbitals. One is lower in energy and one is higher in energy. This is a bonding orbital and this is an anti-bonding orbital. So after we draw the molecular orbitals, then we take the number of electrons that we have, and just like with regular atomic orbitals, we're going to put them in the lowest energy orbitals first. So I have a total of 2 electrons, 1 from this atom and 1 from that atom. And now I'm just looking at these molecular orbitals in the center, and I have room for 2 electrons in this bonding orbital, and so they're going to go in there. If I had a 3rd electron, it would have to move up here, but that's not what I have right now. Yes?
So for the anti-bonding, why does that necessarily occur? Like, why is there...
That's an excellent question. Why does that happen? Why does it occur?
Because the bonding makes sense.
Yeah.
But as far as the anti-bonding, it's like...
Well, when we combine these 2, they can combine in a way that makes it better or worse.
Right.
And they do both.
2 possibilities.
There's 2 possibilities.
Can they occur? So they can...
They do occur at the same time.
Okay.
So when they combine, you get the better situation and the worse situation, both of them, the lower energy and the higher energy. And
It depends on the spin initially.
well, actually, it doesn't have anything to do with the spin of the electron, because the orbitals are going to do this irregardless of what the electrons are doing. And it's a little bit hard because we're trying to approach this really from the surface, just skimming the surface to get an idea. And then when we start to probe and ask questions, which are excellent questions, then those become difficult to answer without getting deeper and deeper into the very, very messy details. Yeah. So some of this you're just going to have to say, well, okay, I could kind of see how that might happen. Yeah.
So how do we know if the molecules go to bonding or anti-bonding?
Well, we don't think of the molecule as bonding or anti-bonding, but the molecular orbitals. And so for every combination of 2 orbitals, you'll have 1 bonding and 1 anti-bonding.
So will we show both of them?
Yeah, it will show both of them just like this. And then we stick the electrons in there. And putting the electrons in here, we see both of these electrons are occupying the bonding orbitals. And so that's going to be lower in energy than the individual atoms were. When electrons go in here, that raises the energy of the molecule and doesn't promote bonding. Does that make sense? A little bit?
Can you go back 2 slides to the bonding orbital? Because I didn't show you more. I showed you yeah, so will the energy going down in this one? This is how
So,
it says.
yeah, so when we have this constructive interference, adding these together, we get a bonding orbital with a lower energy. A bond will form if the energy of the molecule gets lower. Balls roll down hills to lower potential energy. This arrow? No, because this is lower energy, higher energy is up here. Okay, so this, yeah, I'm glad you asked though, because I'm sure somebody else had the same question. My pointer's stuck. Okay, these guys over here. So these are at a certain energy, and then when we come over here, they go down. Yeah, that's all it's trying to show. And then with the anti-bonding, here's our energy, and when those combine, the energy goes up, and the molecular orbital is higher in energy. So if we look at this molecular orbital diagram for hydrogen, what I got ahead of myself with is if we want to look at the bond order, we're going to take the number of electrons that are in bonding orbitals. There are 2 electrons in this bonding orbital. And I'm going to subtract the number of electrons in anti-bonding orbitals. Here there are none. Minus 0. And then I'm going to divide that by 2. And that gives me my bond order. And this is just a way of comparing, is this one more stable or less stable than other types of bonds? It would be the number of atoms. It's always going to be 2 because we're only going to talk about 2 atom molecules. So, like I just showed you, this bond order, the number of electrons in bonding minus anti-bonding, because the bonding orbitals promote bonding and the anti-bonding oppose it. And so we're subtracting those away and then taking the average, and that gives us a number. If this bond order is positive, this is positive, a chemical bond will form. It tells us the overall energy is lower. With H2, it's like, well, why even do this? It's so simple. But when you get more complicated and you've got electrons all over the place, you can't just look at it and see, oh yeah, this is going to be lower in energy, because you've got bonding and anti-bonding, and it gets more complicated. So we have this for the more larger molecules. The higher the bond order, the stronger the bond. If you have a bond order that is 0 or negative, then the bond will not form. It just will not form.
So you were saying earlier, if we have 3 electrons, one of those electrons would go in the anti-bonding
Right.
orbital.
Mm-hmm.
And three and up, I assume.
Well, yeah, you can fit 2 in the bonding orbital, and then you could fit 2 more in the anti-bonding.
And that's for hydrogen.
For hydrogen,
Yeah.
that you'd have to have 2 extra electrons in there. And then beyond that, the electrons would have had to come in p orbitals, and so we're going to look at how the p orbitals will combine. Let's look at He2. So diatomic helium. This doesn't exist. But we could imagine what would its molecular orbital diagram look like. So here's a helium atom, 2 electrons in the 1s orbital. Here's the other one. And again, we're combining 2 1s orbitals. We get a bonding orbital and an anti-bonding orbital. And we have a total of 4 electrons, 2 from each atom. And so we put 2 in this first lowest one, and then the next 2 go up here. And when we calculate the bond order for this, there's 2 in bonding orbitals and 2 in anti-bonding orbitals. You subtract there, you get 0. 0 divided by 2 is still 0. The bond order is 0. Which says this will not form. It's not going to be stable. And it isn't. Because this combination does not lower the energy of these 2 atoms. And so it's not going to happen. The bond only forms if the energy is lower. Any questions? Let's look at He2+. We're going to look at some weird ions and molecules here. So He2 plus, so that would be two helium ions, and the positive charge means we're missing an electron, right? So again, each of these atoms only has electrons in a 1s orbital, so we look at the combination of those, a bonding orbital and an anti-bonding orbital. And then we're going to look at the total number of electrons in this He2 plus ion. It's a total of 3 electrons. We'll say there's 2 from this one and 1 from that one, 3 electrons. So 2 electrons will go in this lower orbital, and then the next one will have to go into this higher one, the anti-bonding orbital. So then we can calculate the bond order of this. There are 2 electrons in the bonding orbital, and then we subtract the number of electrons in the anti-bonding orbitals, and we divide by 2, and that gives us a bond order of 1/2, which is small, but it's still positive, and this ion actually can exist. Right. Because a bond order of 0 means that this does not lower the energy. A negative bond order means making this bond actually raises the energy. Some of these very weird things we're looking at here only exist under extreme situations. You're not going to find He2 plus ions floating around in the air. They're not going to exist there. But on the surface of the sun, maybe so, right? So summary of what we talked about so far. So we approximate the molecular orbitals as linear combinations of the atomic orbitals. We take the 2 orbitals, we add them. We take the 2 orbitals, we subtract them. The number of molecular orbitals that are formed is equal to the number of atomic orbitals. Number of molecular orbitals equals the number of atomic orbitals. So like with the valence bond theory, when we were hybridizing orbitals, you start with 2 orbitals, you end up with 2 orbitals. Conservation of orbitals. When you have 2 atomic orbitals combine, they form 2 molecular orbitals. One is lower in energy and one is higher. One is bonding, one is anti-bonding. It's sort of like, the cartoons where they've got the little conscience on one shoulder and the other, and one's the little devil and one's the little angel. One's promoting good and one's promoting evil. It's kind of that idea. When we put the electrons in the molecular orbitals, we're going to follow the same pattern we did with just the regular old orbitals. We're going to fill the lowest energy ones first with up to 2 spin-paired electrons. If we have orbitals with the same energy, they're going to fill singly first with parallel spins, and then they'll pair up. And then stable bonds require a positive bond order. There has to be more electrons in the bonding orbitals than in the anti-bonding orbitals, is what it comes down to. Okay, so here's a practice one. Use molecular orbital theory to predict the bond order in H2 plus. Is that bond stronger or weaker than the H2 bond? Well, we'll save that question for the end here. And we'll just look at the bond order for H2 plus. So we always do energy going up on the screen. And what I'm going to do is I'm going to draw the atomic orbitals that my 2 atoms have. And so here I've got hydrogen, and here I've got a hydrogen, and this is a 1s orbital, and this is a 1s orbital. Here I've got H2 plus, which means I'm missing an electron. So normally we would have, normally we'd have 1 electron from each hydrogen atom. Because this is a positive ion, one of them is missing the electron. It doesn't matter which side you put that one on, so bye-bye electron. So technically this guy over here is an H plus. And then I'm going to look at combining these 2 orbitals. When I combine them, I get 2 more orbitals. One's lower in energy, one's higher. So one's going to be lower, and one's going to be higher. How do I do that? Up here. And then we should be able to label these. When s orbitals overlap, they always form sigma. S and sigma, same letter, right? So we call this a sigma 1s orbital because it's the overlap of two 1s orbitals. This one is an anti-bonding orbital, and so it's a sigma star 1s. So we've got atomic orbitals on the left and the right, and our molecular orbitals are in the middle. Everybody with me? Kind of. So just maybe to try to make you feel better about this whole topic, my goal in this is not that you become proficient in drawing molecular orbital diagrams and predicting bond orders. My goal here is that you get the idea of this theory so that we can look at a benzene molecule and understand how those electrons can be delocalized over the whole thing. We can look at ozone or another molecular ion that has resonance and understand how can that be? How can you have a 1.5 bond? Well, you can't have a 1.5 bond. What happens is the orbitals are actually delocalized over the whole molecule. So that's the goal here. But we just have to trudge through some of this stuff. So I have one electron here, right? So I'm going to put one electron in my molecular orbitals. It's going to go in the lowest one. And that's the molecular orbital diagram for H2+. And then it's asking us for the bond order. I'm going to call it BO. It's not body odor, it's bond order. How many electrons, and here we're looking at this part right here. How many electrons in bonding orbitals? 1. How many in the anti-bonding orbital? 0. I'm always going to fill the lowest energy orbital first. And the bonding orbital will always be lower in energy than the anti-bonding, so it will fill first. So when I do this, I get a bond order of 1/2. Earlier we looked at H2. For H2, the bond order was 1. For H2+, the bond order is 1/2. Is the H2+ stronger or weaker? Yeah, it's weaker. This is lower than this. So that predicts that the H2+ bond is weaker than an H2 bond. Any questions?
So the quantitative number for each bonding order, it's the same as strength.
Yeah, bond order is a little bit like a formal charge or oxidation state. It's a number that we kind of assign based on criteria to give us some way of comparing things. Yeah, that's really all it is. Okay, what's next? So we just covered period 1 in the periodic table, which was hydrogen and helium, right? Great accomplishment. So now we're going to look at elements in period 2. And what we're looking at here, period 2, that's the second row on the periodic table, homonuclear, meaning the same nucleus so the same element, diatomic molecules. So these are two atoms of the same element forming a molecule, okay? Again, we're only going to look at valence electrons. We're not going to look at core electrons. So we get into the second period and we look at lithium. Lithium has one electron in its 2s orbital, right? And the other lithium, one electron in the 2s orbital. The 2s orbitals are going to combine in the same way that 1s orbitals did. They'll make a bonding orbital and an anti-bonding orbital. Here this is sigma star 2s and sigma 2s instead of 1s. We have one electron here, one electron there, so we put a total of 2 electrons. They both fit here. We can calculate the bond order, and we look at there's 2 electrons in the bonding orbitals, there's 0 in the anti-bonding orbitals, and that gives us a bond order of 1. Yes?
Why did you put the 2?
This 2s?
No.
Why did I put this 2 or this 2? No? Well, if it comes to you, please ask, okay?
So I can't ask some questions. So like,
Okay.
do you choose the farthest orbit when determining its molecular orbit, whether it's antibonding or bonding?
Well, what I'm doing here is I'm looking at valence orbitals on the atoms,
Okay.
okay? And so if we look at the the electron diagram for lithium, it has 3 electrons, right? Total of 3 electrons. And so it's going to be like this. This is the valence electrons, and so this is all we're going to look at. We're going to ignore everything down below. Okay? So that's why I've got the 2s orbitals. Yeah. Any other questions? What about Be2? Just go across the periodic table. Well, if we look at beryllium on the periodic table, it's in group 2a, and so we know that it has 2 electrons in the 2s orbital. Those are its valence electrons. So drawing the orbital diagram here, again, we've got the combination of 2 2s orbitals. We get a bonding orbital, an anti-bonding orbital. But now we have a total of 4 electrons. So we've got this same sort of structure here in the middle, but putting 4 electrons in, we put them in the lowest energy ones first, and then in the higher ones. And here, they fill both of them completely. And so the bond order would be 2 electrons in bonding orbitals minus 2 electrons in anti-bonding orbitals divided by 2, a bond order of 0. It doesn't exist.
So if it was Be2 plus, then it would be 1 in anti-bonding, 2 in
Yes.
bonding.
So if we had Be plus, one electron missing, so this would be a positive charge, then we'd have 2 bonding orbitals, 2 electrons in bonding orbitals, and only 1 in anti-bonding. And so then when we do that, we get 1/2, which predicts that the Be2 plus should be stable. Well, when we go to the next element, boron, now we're getting into p orbitals. So we have to look at how p orbitals are going to combine. So just so that we don't get confused, we're going to say that the axis that's going between the nuclei, we're going to call this the x-axis. We're just always going to have that be the x-axis, and then y and z would be perpendicular to that. But x is the internuclear axis. It's between the nuclei. So if we combine two px orbitals. Those are the p orbitals that lie along the x-axis. In a p orbital, one node is negative and one node is positive. And so it's a little easier to see how these might combine rather than the spherical ones where you can't see the other phase. So we put these together in phase with the blue and the blue, and then that part gets bigger, right? And these parts get smaller. And so now we have increased density between the nuclei. If we put these together out of phase, you could imagine subtracting or flipping this one around so that you've got blue here and red there, and you combine them. The part in the middle is going to partially cancel out, and so you're going to get more density away from the nuclei, and this is going to go against bringing these nuclei together. So again, we're taking two orbitals, we combine them, we get one that's lower in energy and one that's higher in energy. I'm not going to grill you on the shapes of these or anything. The only reason for showing you this is so that you can say, well, I could see how that could happen. And if you don't see how it could happen, you could just believe me and go with that. Yeah. No, we're not talking about spin on electrons. We're talking about the phase of the orbital. So the orbital is a region of probability. The orbital is there whether there's actually an electron in it or not. And like a wave, so if I have a standing wave, and I take a picture of it, I could catch this side of the string above the median line and this side below. So this is the positive phase and this is the negative phase. I could also have it going the other way, where I've got the negative over here and the positive over there. And so with water waves, those cancel each other out completely. These are not that simple. They don't actually cancel each other out, but the idea is similar. Okay? So in these p orbitals, one node is a negative phase and one's a positive phase. So we can kind of see how that works with standing waves on a string, and yet we can't because this is extremely simplistic. Well, what about those other two p orbitals that are not in line with the nuclei? So here's py for each of these. We got the nuclei in the middle here. Those other orbitals were going this way. So these are coming in and out of the paper, or the page, the screen. I'm stuck on paper. I gotta get over that. So what about when these things combine? Well, if these combine in phase, we get a big red part here and a big blue part back there. And again, this promotes electrons being between the nuclei. If we subtract them or add them out of phase, then we get something like this, where now the electron density is away from the nuclei, and it does not promote bonding. These orbitals are not round if we look at them from the end, right? If we look at this from the end, let's just imagine what we might see. So if I'm looking at them from the end, what I might see is, let's get this right. If I'm looking at it, I'd see maybe something like this and something like this, right? I'm looking this way and I'm seeing two pieces. This other one, if I'm looking from one nucleus to the next, what I'm going to see there is round, fat, blue thing. And, if I want to put the red in there, it'd be a little smaller thing in the middle, right? I see the little bit of red and the blue, and I can't see the other red. I'm looking down. It's symmetrical, it's round, it's like a sigma. These are sigma orbitals, just like the s orbitals were. When these overlap, though, they add side to side, and we call these pi orbitals. This is very much like the valence bond theory bonds, where we had a sigma bond was an end-to-end overlap, and the pi bond was side to side. So this is like a pi bond where we have side-to-side overlap. So these are pi orbitals. Again, star is anti-bonding, without a star is bonding. This is a 2p, star and not star. Then there's another set of p orbitals in the z-axis, and they combine in that side-to-side way, and they're going to form a bonding orbital and an anti-bonding orbital. And again, the shape of this from the internuclear axis is not round, and so these are pi orbitals also. These orbitals have the same shape and the same energy as the pi orbitals that we had in the previous slide. The only difference is their orientation in space. So when the three p orbitals combine, we have sigma orbitals and pi orbitals, and the sigma and the pi don't have the same energy. And the relative energy ordering is not the same for all of the elements. It would be determined computationally. We're only going to be concerned about the first two periods of the periodic table. And what we find is that boron, carbon, and nitrogen, B2, C2, and N2, have a different order than oxygen, fluorine, and neon. The typical energy ordering is this one. This is what you could consider normal. Sigma bonding is the lowest. Sigma anti-bonding is the highest. They're at extremes. And then pi bonding and pi anti-bonding are in the middle. So when we draw that out, this is the expected order. So this is normal. There's our S, and made a sigma and a sigma star. And here are three p orbitals. We're going to get two of them that overlap and form a sigma bond, sigma orbital, and a sigma star. And then the other two that are going into the screen and up and down do a side-to-side thing and make pi molecular orbitals. So there's two of those bonding and anti-bonding. The ones that overlap end to end and make the sigma, that's a better overlap, right? And so that's one of the reasons why we can think of that as, well, it is lower, but kind of trying to figure out a reason other than because the computer told us. So any questions about this one over here before I talk about that one? So this is regular order. This is for boron, carbon, and nitrogen. And so we can use the letters, the element symbols there, B, C, N. Be careful now. The ordering here is different. These three, boron, carbon, and nitrogen, do something different with the order. Anything else, I expect you to do this, but these are weird. So how are they different? Well, sigma star is still at the top, pi star is next, and the difference is the order of these two, right? So what happened here is that the order of these got reversed. Instead of the sigma being lower, the pi is lower. I wish it was all the same, but you know, I didn't invent all of this, so. So why does that happen? There's increased mixing between the 2s and the 2px orbitals for boron, carbon, and nitrogen. Those mix more, and so that's how this order, this order gets reversed. I don't completely understand that myself. It's not really critical for anything, and so I just don't bother with it. But there, it's in the book, I told you about it. So here we have molecular orbital diagrams for B2, C2, N2, O2, F2, and NE2. And again, we're looking at valence electrons. So we've got a 2s orbital from each of the two atoms combining and makes a 2s bonding and a 2s antibonding. And then there's 3 p orbitals from each atom, and when those combine, we get a total of 6 orbitals. And the order here is that the pi bonding is lower in energy than the sigma bonding. And then we have pi star and sigma star. So be careful now. These are the 3 with that irregular order. And then over here, for these guys, OF and NE, they have the regular order where the sigma is lower than the pi. We can take the number of electrons and stick them in, and we can look at bond orders. And so what we see is the bond order increases as we go from boron, carbon to nitrogen. Bond order of nitrogen 2 is a bond order of 3. That's very high. And that corresponds with bond energies and the bond length. Bond length gets smaller as the bond gets stronger. Higher bond order, stronger bond. The order of those orbitals switches here, and as we move across, O2 has a bond order of 2, F2 has a bond order of 1, NE2 has a bond order of 0. Which, yeah, we wouldn't think that NE2 would exist. It's a noble gas. Why would it do that? It wouldn't. Again, now we see the bond order decreasing and the bond length increasing. I know. That's an excellent question. Basically, you're asking, how am I going to test you on this? Right? I am not going to make you draw these things from scratch, because I don't see the point in that. There are multiple choice questions in the test bank where they've got several different molecular orbital diagrams. You pick the right one. Or, as an open-ended question, I can give you a molecular orbital diagram without any electrons in it, and just have you fill it in and tell me what the bond order is, or something like that. I think there's some questions where I give you a couple of weird things like O2 and O2 plus and Fe, F2 minus or something, and say which is the stronger bond. And so then you would fill in the provided molecular orbital diagram with the number of electrons and calculate the bond orders. I won't intentionally try to trick you with this be careful now business, but it could happen by accident. Okay. So we know from experiment that oxygen is paramagnetic. It's attracted to a magnetic field. And so I actually have a video here to show you. I'm going to show you the long version, because the short version is like super short. I don't. Oh, there is sound. Paramagnetism of oxygen, starring Daniel.
So we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled dewar. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet. Then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
So the oxygen from the tank is passing through that coiled tube inside the liquid nitrogen, so it's getting really, really cold. And it's cold enough that the oxygen condenses into a liquid. It's really cold. And that is liquid oxygen. Yeah, and the tube's so cold that it's just, getting all sorts of water from the air freezing on the outside of it. So that's liquid nitrogen. It looks like water just pouring through the magnet, right? And here's liquid oxygen. See that? It sticks. Oxygen is paramagnetic. It is attracted to that magnetic field. Nitrogen is not. Diamagnetic means it's not attracted because all the electrons are 2 by 2. Paramagnetic is attracted. So I called that the long version for a reason. This is the long version. That's the magnet. It's really, really strong. That's not what I meant to do. I don't like this computer. Hey. Anybody have any comments? Say that again. There's paramagnetic and diamagnetic.
No, but this one is from the last chapter where we were pairing up things on the orbitals.
It's still the paired electrons and the unpaired electrons.
It's not paramagnetic. Okay. Oh, fine.
Yeah, I don't know. Yes. Pardon me? If you were to drink liquid oxygen, your mouth and your tongue would freeze pretty much instantly. Yeah. Did any of you go to the Halloween science show that we had? No. They did a lot of fun stuff with liquid nitrogen. And liquid oxygen is similarly cold. And so one of the fun things they do is they take like a rose and they stick it in the liquid nitrogen. And you pull it out, and it looks fine, and then you tap it on the counter, and it shatters. The other fun one is Christian puts on a pair of gloves, and he has a hot dog in one of the fingers. And so he sticks it in the liquid nitrogen, and he's carrying on like, oh, my finger, and then he hits it with a hammer, and there's ketchup in there, and it's really gross. But when things get as cold as liquid nitrogen and liquid oxygen, they become very, very brittle. You stick a rubber ball in there. Rubber ball looks fine. You bounce it, it'll shatter. One of the coolest demonstrations my college physics professor did, took half a banana and stuck it on the end of a wooden rod so it kind of looked like a hammer. Can you imagine this? Froze the banana in liquid nitrogen and used the banana to hammer a nail into a piece of wood. I know, just like such fun stuff. But that would not be good in your mouth, right? Instant frostbite, really bad frostbite. Okay, so we just saw the video demonstrating that oxygen is paramagnetic, right? In order for it to be attracted to that magnetic field, there has to be some unpaired electrons in an O2 molecule. Well, if we look at the Lewis model for oxygen, here's the Lewis structure. Do you see any unpaired electrons? I don't. They're all paired up, right? Everything we've been doing so far everything's all paired up. Here is the valence bond diagram for O2, where we have a sigma bond here, and then we have a pi bond here. Are there any unpaired electrons? Nope. Both of these models predict that oxygen is diamagnetic. It should not stick in that magnet. Ah, shoot, I thought I had, oh, I know what we can do. We can just go back. We can just go look at this one. I don't have to draw it again. So here's O2. This is the molecular orbital diagram. Do you see unpaired electrons? Yep, right there. So in the anti-bonding pi orbitals, there are two orbitals that are half full. And that is how oxygen is paramagnetic. We look over here at nitrogen. It's not. It's not diamagnetic. I mean, it's diamagnetic. It's not attracted. And that's fluorine. Sorry. Wrong way. Nitrogen. If we look at nitrogen, it's still all paired up. Any questions? Why don't we see them in these other models?
Yeah.
Because these other models are limited. They're not giving us the whole story. They are much simpler. Valence bond theory, I think most of you were pretty engaged with on Monday. The best I've ever done. It was really fun for me, thank you. We can imagine how these things overlap, and we can get our mind around that. Molecular orbitals, what we're talking about here, we're just scratching the surface, and already we're like, oh my goodness, I have all these questions that she can't answer, right? Because she doesn't know what they are. It's really, really complicated. It goes more in depth, it's more rigorous, and it fixes some of the holes in these other models. So why don't we use it all the time? Because it's a pain in the butt, right? So we use Lewis theory if Lewis theory works. So Lewis theory works for a lot of things. And where that doesn't help us, then we look at valence bond theory, the next more complicated thing. That explains some things that Lewis theory doesn't. But then there are some situations where we have to understand that molecular orbital theory can explain what we're observing. So that's kind of the point here. Let's try this one. Draw a molecular orbital energy diagram, determine the bond order for the N2 plus ion, and then there's some other questions. Okay. So to do this, I'm looking at nitrogen. This is nitrogen and that's nitrogen. And N2 plus, one of them has to be have a positive charge, so I'll make over here. And nitrogen has its valence electrons in the second shell, so I've got 2s here, and then I'm going to have some p orbitals. I've got 2 p orbitals. And then to combine them, okay? Like I said, I'm not going to make you do this on an exam, but I'm going to talk you through it just to help you understand it. How many valence electrons does nitrogen have? 5, right? So I'm going to put 5 electrons in here. 1, 2, 3, 4, 5. And this other one I've labeled N plus, because it's short an electron, right? So that's going to have 4 valence electrons. 1, 2, 3, 4. And really that's just so that we have the right number of electrons later. Yes?
Is just the regular N ion, and that's supposed to be 2s over there? Or?
Yeah, it is, thanks. Yeah, I don't know why I wrote a P here. Thanks for catching that. I could lie and say I was just seeing if you're paying attention. I screwed up. So the 2s orbitals will overlap, they'll combine. When 2 orbitals combine, they make one that's lower in energy and one that's higher in energy. So one down here and one up here. That's kind of ugly. The s orbitals make sigma orbitals. So this would be labeled sigma 2s, and this is anti-bonding sigma star 2s. And it can be helpful to draw some lines to see where did these things come from. And then combining the p orbitals. One pair of p orbitals makes a sigma pair of orbitals, and the other 2 make pi, right? And be careful now, nitrogen is one of the weird ones. So what happens with nitrogen, and as usual, I didn't give myself enough room. I can fix that though. Just going to give myself a little more space. So what we normally expect is the sigma is the lowest and the highest, and for boron, carbon, and nitrogen, the lower 2 are reversed. Well, it's one element, but it's 2 atoms of the same element. So for boron, carbon, and nitrogen, the pi 2p is lower in energy than the sigma 2p. And then the pi star 2p, and then the sigma star 2p. And yeah, there's too many letters on the other side to draw the lines. So on an exam, I might give you this part in the middle. Of course, it would be nice and neat and not all sloppy and ugly. To figure out the bond order for N2+, I have to know how many electrons do I have. Again, it's all valence electrons. I have 5 electrons from this one and 4 from this. I lost an electron for the positive charge. So that's a total of 9. And I'm going to fill these molecular orbitals the same way I filled atomic orbitals. Start with the lower energy ones first, pair up when I need to. So 1, 2, 3, 4, 5. Now this one can have its own orbital, 6. And now they have to pair up. 7, 8, 9. So this is saying, do we expect the bond to be stronger or weaker than in the N2 molecule? Well, how would the N2 molecule be different as opposed to N2 plus? It would have one more electron, right? That one electron would go in here. The next electron would go in there. This is a bonding orbital. So adding another electron in this bonding orbital is going to make the bond stronger. Right? We could calculate bond order. So here's our N2 plus. Let's look at the bond order for that. N2 plus. Bond order equals how many in bonding electrons? Bonding orbitals, I'm sorry. This is, oh gosh. This is bonding, and this is bonding, and this is bonding, right? So you count the arrows in there. 1, 2, 3, 4, 5, 6, 7. 7 electrons in bonding orbitals. How many in antibonding orbitals? 2. This one is antibonding. So 7 minus 2 over 2 is 5 halves, or 2.5. If I make it N2 rather than N2 plus, then I'm adding, I'm going to make it a big fat electron. I'm adding an electron in there. That's where the next electron would go. So with this diagram, how many electrons are in bonding orbitals? 8, right? And how many in antibonding? Still 2. Divided by 2, and that's going to give me 3. The bond order here is larger than that one. That tells me that this bond is stronger. This is asking, do you expect the bond to be stronger or weaker than the N2 molecule? Well, it's going to be weaker. This one is weaker than that one. Yes? Where did I get the number 9 from? That's a good question. I have, in the N2 plus, I have 2 nitrogen atoms, and I'm missing an electron. So we could do it the Lewis theory way and just, count up valence electrons. I have 2 nitrogens, they each have 5 electrons, and then I have a positive charge, so I'm going to subtract 1, and I end up with 9. Okay? Yeah. And then the other question is N2 plus diamagnetic or paramagnetic. So that's without the purple arrow. It's paramagnetic. And again, those words are so confusing. Di means 2. Noah took the animals 2 by 2, right? So N2, as I've got it drawn here, is diamagnetic. Everything's paired up. When I get rid of this electron, that's paramagnetic because I have an unpaired electron. Any questions? I'm going to take a little tiny peek at heteronuclear diatomic molecules. So this is one of my favorite compounds. No! There's this girl in the other class. I really need to hire her to come in and be my laugh track for all my classes, because she would have just busted up when I said that. But she's not here today. No, NO. So here's the diagram, and I'm not going to ask you to draw anything like this. Here's the nitrogen atom, and here's the oxygen atom. Because these are different elements, the energies of their orbitals are different. And so then when we combine things, they can get a little, skewed. The low energy atomic orbitals contribute more to bonding, and the high energies contribute more to the anti-bonding. So this is contributing more to anti-bonding, and this is contributing more to bonding. If we look at hydrogen fluoride, nitrogen and oxygen are right next to each other in the periodic table. They're really similar in size and electronegativity. Hydrogen and fluorine are quite different from each other. And here, the fluorine is so electronegative that its atomic orbital 2p is lower in energy than the 1s orbital in hydrogen. It's weird, right? So then when hydrogen and fluorine bond, it's one of these p orbitals from fluorine with the s orbital here, and they're going to make sigma and sigma star, and they're going to share 2 electrons in there, and then the others will go in these non-bonding. They're not anti-bonding. They're just like nothing. They're neutral. I don't want to do that one. Okay, ozone. We talked about ozone when we talked about resonance. And so here's the Lewis explanation for resonance. Basically admits I can't explain it. It's between these two things, right? Because experimentally we know that the bonds here are of equal length and equal strength. And yet when we draw this, we have to choose single bond, double bond, or double bond, single bond. If we look at the valence bond model, it doesn't do any better, which is why we didn't even mention it when we were doing it. Here we can put the double bond here and the single bond over there, or we can do the reverse, but we can't show what's actually happening. So this is molecular orbital theory. In molecular orbital theory, we combine the p orbitals from all 3 of those oxygen atoms, and they form molecular orbitals that go over the entire molecule. And so the electrons are shared over the whole molecule. And that's how they can be shared equally and have equivalent bonds. What? Well, let's go back and talk about this one. The Lewis one. So what we want to show here is that we have sort of, well, this is oxygen and single bond, and so there's a pair of electrons in each of those, and then there's another pair of electrons that instead of being a double bond on one side or the other, that pair of electrons is sort of both on both. So you could kind of think of it as one electron going here and one electron going there. But then what do you do with the lone pairs? It gets really messy. Well, the resonance structure, remember, is not vibrating back and forth between the two structures. The actual structure is a combination of all the resonance structures. Just like the dogs, right? German Shepherd, Golden Retriever, their puppies don't change back and forth. They always look the same. They look like a combination of their parents, right? And so the actual molecule is neither of these. It's a combination of both of them. But we can't illustrate it with either of these theories. In molecular orbital theory, we can take 3 pairs of electrons and have them be shared over the entire molecule. And so that's what's going on here, is there's a pair of electrons from each of the bonds, and then there's another pair of electrons that would make the double bond on one or the other side, but that pair of electrons is shared over the entire molecule. Does that kind of make sense?
So in the last one, the last slide, you had like that red one.
Mm-hmm.
Would that be the substitute of that? Like it could be one of those two.
So this pi bond That's the pair of electrons that in molecular orbital theory is getting shared over everything. Although actually all of the electrons are being shared. In valence bond theory and in Lewis theory, the bonding electrons are localized between two atoms. And so this pair of electrons occupying these two overlapped orbitals, those electrons are between the two oxygens. And the second pair of electrons in these two p orbitals that are overlapping side to side, those are localized between these two oxygen atoms.
So what's that other like behind the proton?
What's this one?
Yeah.
So this is the other oxygen atom. So this oxygen would be sp2 hybridized, and we have the unhybridized p orbital. And so it's making a bond with this other oxygen, a sigma bond, overlapping with its p orbital. And then this would be a lone pair. That would be the lone pair here. So any other questions about this one? Okay, here's the real reason we had to talk about all of this. This class is a prerequisite for organic chemistry. Organic chemists care a great deal about resonance structures, delocalization of electrons, because it has a huge effect on the stability of molecules and how they react with each other. So molecular orbital theory explains resonance. A very common molecule you'll see in organic chemistry is this one. It's called benzene. And it's got alternating, as we draw it in Lewis structure, it has alternating double and single bonds between the carbons. And so you can draw it this way or you can draw it that way. So we have these two resonance structures. But in actuality, all of those bonds are identical because the real structure is a combination of these two. The real structure is going to look more like this, where the second pair of electrons from these bonds is more like this, sort of like a pi bond, but over the entire molecule instead of localized between two atoms. And this is much, much more stable. Benzene is very, very symmetrical, kind of like a snowflake. You know, it's got six things hanging off the end. And we've got 6 identical carbon-carbon bonds. And that comes from those 2p orbitals making delocalized pi molecular orbitals.